Welcome to Welcome to the Innovators of Cognitive Neuroscience speaker series. My name is Emma Laurent, and I'm a first-year graduate student at Harvard University. Thank you so much for joining us this morning for the next talk, or afternoon, depending on where you're tuning in from, for the next talk in our series. Before beginning, we want to acknowledge the Indigenous in the lands from which we are joining today's talk. So I'm speaking to you from Topanga, California, which is located in the Santa Monica Mountains of Los Angeles. Here and the surrounding areas are marked in name by the peoples from whom this land was taken, the Tongva people. This canyon was the westernmost border of the Tongva territory, with the Chumash tribe occupying the coast from Malibu northwards. So I actually learned that Topanga means literally where the mountains meet the sea in the Tongva language, and has the root topa, likely originating from the Chumash language. The institutions and landmarks bearing this name should remind us of our land's traditional occupants. Please use the link I've just sent to the chat to research and reflect on the Indigenous lands from which you are joining us. Through the acknowledgement of past harms, we step towards more equitable and humane futures. On behalf of all the students and postdocs on the organizing committee, I'm excited to welcome you all to today's Innovators in Cognitive Neuroscience seminar. The organizing committee together represents a consortium of colleges and universities, including Dartmouth, UPenn, Yale, MIT, Princeton, Harvard, Columbia, and Gallaudet, that are committed to highlighting advances in cognitive neuroscience research. We acknowledge the privilege of these institutions and wish to make the science discussed here available and accessible far beyond the ivory tower of academia. With the consent of our speakers, we plan to make these talks publicly available on our website, and our seminars open to anyone interested. Just a quick note to those of you who are new to this series. After the talk is over, we're going to move over to or after the preliminary Q&A, we're going to move over to a trainee Q&A. And this is a space for anyone to ask additional questions that weren't answered during the talk. And I've just posted the link in the chat, and I'll also post it one more time once the presentation is ended. And this brings me to our lovely host, or our guest. Sorry, I'm the host. Today, we're fortunate to have with us my friend, Dr. Keith Doling. I first met Keith in the Popple Lab at NYU when he was a fourth-year graduate student, I believe, and I was an RA. He was first described to me as the perfect graduate student, independent, creative, and ambitious, while patient and generous with his time. I have benefited directly from his generosity and expertise, having sent many an exasperated email asking for advice on eliciting steady state evoked potentials and the like. All this to say, Dr. Doling is not only an accomplished scientist, but a skilled mentor. Dr. Doling received his bachelor's degree in cognitive neuroscience at Harvard University in 2011. He then went on to complete his graduate work with Professor David Popple at NYU and received his PhD in cognitive science in 2018. He has since moved to Paris and is a postdoctoral fellow at the Hearing Institute at the Institut Pasteur in the Auditory Communication and Cognition Lab. His research interests center on the temporal and content dynamics of processing speech and music. With the use of modern neuroimaging and computational modeling techniques, he investigates the role of neural oscillations and their capacity to support basic functions such as segmentation, temporal prediction, and attention. Dr. Doling has won numerous accolades, including, among many others, the Fison Foundation's postdoctoral fellowship in 2019, SFN's Neuroscience Scholars Fellowship in 2015, and the NSF Graduate Research Fellowship in 2014. Finally, as I have had the unique privilege of experiencing firsthand, Keith is also a talented musician trained in jazz and classical on both the bass and piano. As we will soon see, his extensive musical knowledge finds its way into his research in exciting and novel ways. Today, he'll be telling us about all of his work, I guess, his research summary on probing the limits of rhythmic processing models in naturalistic settings, namely in speech and music. Please join me in welcoming Dr. Keith Doling.
Wow, what a great introduction. Thank you so much, Emma. It says I cannot start screen share while the other participant is sharing.
That would be me, and I am stopping sharing. There you go.
Okay, perfect. All right, so I will share my screen, start up the slideshow. Just want to confirm that everyone can see the entirety of my screen.
Yep, you're good.
Okay, great. So first I want to thank the Innovators Talk seminar series for inviting me. It's a real honor to be involved. and to be included in this kind of process. I want to thank Emma, who's been a great guest, a great host now, right? Again, I'm the guest. And of course, Adam, and our interpreters here, Kyle and Heidi and Lovita for captioning for us. This is really an amazing series. I know the first time I saw the Danny Bassett talk, and they did the sort of recognizing the lands of the Native Americans, I knew this was a very different kind of series than we normally see in science. It's super humbling and super important for us to remember where we are and how we got here. So with that in mind, I want to start by highlighting the charity that I've chosen to support for this particular talk, which is the Critical Resistance Movement, which is a police and prison abolitionist group. So there are lots of reasons why to think about police abolition. There are many astonishing statistics about police brutality and the treatment and sheer number of prisoners in the United States. But I don't really want to focus on the numbers today. I'd rather focus on the system as a whole. Even if George Floyd hadn't been murdered, his assault and subsequent processing would still be immoral. And so the system and the way that it works is, to me at least, broken. And so I just want to highlight a couple ideas about that and just sort of starting points for people to start thinking about this in different kinds of ways. And one key distinction that I've sort of found as I've been sort of looking through this literature is this distinction between crime and harm. Typically we think of the police as being necessary for catching and punishing criminals. But crime is a social construct. It's criminalization of behaviors is something that's decided by sort of the people that are in power and can be used to police mostly poor and immigrant communities. Things like laws against loitering or non-violent drug offenses or broken window policing. The solution to these has become punishing punishing people through caging, and it doesn't actually seem to fix anything, and it seems to just cause more harm than it solves. So this is in distinction to something like harm, which is really more the sort of pain and violence that's inflicted on another by another person or the government. And I think the goal of our justice system should be towards addressing harm, rehabilitating victims, and holding perpetrators accountable for their actions in a way that doesn't make things worse. So that's point one. Point two is that the police system that we currently have is deeply intertwined with the maintaining of racist status quo that we've had in the United States through both capturing escaped slaves before the Civil War and including being involved in lynchings during the Jim Crow times, and beating of nonviolent protesters in the 1960s, and on and on and on. And if you were to be talking about an organization that had this kind of history, that wasn't government sanctioned, but was sort of a private organization, the talk wouldn't be about whether or not you should ban chokeholds. The talk would be about dismantling this organization and creating a new social contract for the people that are involved. And so that's, for me, the goal of police and prison abolition. And for students and postdocs who might not necessarily have the money to donate a ton financially, I suggest that you donate your intellect and spend time looking at this kind of literature, learning more about the process and talking about it with your friends. And if you don't want to talk about it with other people, or you're welcome to talk about it with me. And I have posted my Twitter and email here. I'm happy to talk about this stuff. I am not an expert, but I think it's an important thing to discuss. So these two organizations that I've highlighted, first is Critical Resistance, which is a chapter-based organization which focuses both on building community-based solutions to avoid altogether involvement with police when problems arise, as well as to build campaigns to end the openings of new prisons and promoting investments in the things that actually do keep people safe, things like housing, education, healthcare, and employment. As I was doing the research on what I should talk about in these couple of slides, I found the Common Justice Organization, which I think is another very useful and important organization to look at, which basically creates an alternative to the prison system, making restorative justice the goal in sort of developing, developing survivor-centered responses to violence and holding violators accountable through meaningful action, both in terms of meeting directly with victims face-to-face if the victims are willing, but also in terms of drug rehabilitation, jobs training, and so forth. And so, this is sort of another way forward. And maybe it's not the perfect way, but it seems to be a look out into another direction. And I hope you guys will spend some time with these ideas and feel free to talk to me about it whenever you like. So now I'll go into the science. And so most of my work has been about how do we predict in time certain rhythms, particularly in speech and music. And I'll give you first an example of what that process really means. So here's an example of sentences which have no spaces between the words. It's analogous to what you have to deal with in speech, because in speech, you're not actually given each individual word separately. They have everything sort of continuously and overlapping. So it's not only that the words are connected, but also the phonemes, and also those phonemes are highly overlapping. So here's the process that you have to do. Take this kind of signal and decode individual words from them without actually knowing what they are. So I've just recorded myself speaking just a small fragment of this sentence. And I'm showing you here the spectrogram of this signal. And what you can see, you might say, okay, actually, Keith, I see white spaces here. There are sort of clear spots where there's sort of no sound. And so maybe this is what you need in order to decode the signal. But actually what you'll find is that the true boundaries between syllables, let's say, are far more varied and more complex than what you see in these white spaces. And so our job is to identify, when those correct chunks are in order to decode both, what and when things are occurring. So how do we do this? Before I answer that, I'm going to give you another version of this problem, which we have dealt with in synchrony in music. And here's an example from the 2008 Beijing Olympics, where 2008 drummers played together in perfect synchrony. I'll just give you a few minutes of this. Okay, so this is a particularly amazing feat to me. And the question, another way of asking the same question, is what does it take to be this guy? One person in this system of 2008 drummers. And so what I'll argue is that you need three important features. One is a perceptual system, something that allows you to hear the sounds around you. Two is a means of reacting to those inputs, so a motor system that allows you to play. And the third most important thing for this particular talk is an internal model that allows you to make your own predictions of timing, right? So if you don't have this, you'll always be late. You'll always be reacting to inputs. And so the idea is in order to be able to really play in synchrony, you have to know when things will occur. So in both speech and music, you have to be able to extract these sort of temporal statistics. And so what is actually in those signals that allow you to do that? Well, it might interest you to know that both speech and music are rhythmic. And what I mean by that is that if you take, for example, a speech envelope and you sort of trace the sort of amplitude volume changes, which is what we call the speech envelope, you can analyze the structure in that signal, and you'll find that there are peaks at about, I'm showing you here in black, about 4 hertz. And so this suggests that there's actually some sort of overall rhythmic pattern, which has some variability, but has some sort of temporal statistics that we can extract. So the same is also true, perhaps unsurprisingly, in music. But what's interesting is that it's not just an acoustic feature, but also a linguistic one, right? So syllables are of the order of about 200 milliseconds long. And that's true across most languages. And again, there's some variability, but we have some feature that we can predict here. So how can we extract that from in the terms of a neural perspective? So it turns out not only is speech and music rhythmic, but also so is your brain. And by that, I mean that there are populations in neural cortex that fire in rhythmic patterns. So here's an example of a population where a sort of raster plot where each little dot is a neuronal spike. And what you can see is that if you look at one particular line, you might not necessarily see the rhythm, but as you sum across this whole population, you see these moments of high and low excitability, which fluctuate in a rhythmic pattern. So these fluctuations occur not just at one particular time scale, but from a wide array, ranging from 40-second long cycles to 600 cycles per second. And what's particularly interesting is that these timescales are maintained across evolution, right? So the same oscillation in a mouse cortex will look pretty similar in the human cortex, despite a huge increase in size, several orders of magnitude increase in size. And so that suggests this is not just the accident of axonal length, but is instead conserved evolutionarily. So we're particularly interested in this sort of 1 to 8 hertz range, sort of delta and theta, and that's because it matches on well to what we see in the musical rhythmic structure and also what we see in resting state and auditory cortex. So here's resting fluctuations in primary and secondary auditory cortex, both showing peaks at around 5 hertz. Now, how do we actually use oscillations in the brain? I'm going to break this down, sort of oversimplify this and break this down into 2 major classes of functions. One is for sort of temporal coordination. An example of that is in the hippocampus, where we all know that place cells are used to code for specific locations in a room or a maze. But what you can find is that not only is the firing rate coding for location, but the timing of firing relative to, say, a theta oscillation will code for the trajectory of the mouse, so where it's come from and where it's going. Another example is in working memory, where it's been suggested that you can hold multiple items in memory by placing them at different phases of a theta oscillation. So in this example, the first item is held at sort of a leading phase, where the last item might be held in a lagging phase. And this is sort of a way of segmenting your items across multiple different items. So that's coordination. Another very popular way of looking at oscillations is in terms of communication between brain regions, right? So here's an example where, let's say you want communication to occur between the red and green region, so they align in phase such that they're both excitable at the same moment in time and therefore can communicate well. If you want instead to inhibit a particular region, then you want to align in antiphase, where the green region might be excitable while the black region is not so much, and so they continually miss each other in time. So these 2 ideas are useful for brain function, but they're also useful for auditory perception in terms of coordination in time for these kind of segmentation and prediction kinds of processes, but also in terms of information selection to select, for example, one particular signal in the sea of sounds that we're listening to all the time. So the question that we ask here is, do oscillations provide the same functions in speech perception that they've been shown to provide in other sort of more internal neural domains? So what would that look like? The idea would be that here's an example of a sentence in speech. The brain would listen to that sound, synchronize to it, and then break it up by the individual cycles, break it up by some sort of specific phase, which can then be fed into a decoder to identify what each chunk actually means. And so I'll break down this talk into 3 main segments. The first 2 is published work, and the last one will be sort of some new, I think, exciting stuff that we've sort of developed on top of this. And so first we'll discuss auditory cortex and whether or not it tracks acoustic rhythms. Second, we'll look at whether that tracking can be supported by a neural oscillator. And lastly, we'll say, if we're in an oscillator world, how do we deal with ambiguity? So all of these segments will be based, for the most part, in MEG data, which allows for magnetometers, so 157 magnetometers in this case, which detect very small magnetic changes in the field. And what we'll see is that you get very high temporal resolution, so you can see millisecond by millisecond how things are moving, and sort of okay spatial resolution. So we have a good idea that the data we're getting is from auditory cortex. And so I'll show you data that comes from these sort of major sensors, which respond well to auditory tones. It's sort of a typical response to an auditory tone. Here's what the actual machine looks like. All of the sensors are housed in this sort of toilet bowl shaped system. We can have audio presented, visual, and we can get button presses from the subject as well. So in this first study, we presented musical stimuli spanning a range of note rates. Here's just an example of a Brahms intermezzo that we extracted, showing you first the sheet music and then a sort of naturally played piece by Murray Pariah in a sort of a spectrogram shape. And so we characterize each one of these pieces by their note rate. Here's an example of a 5 notes per second condition. And I'll show you sort of, and so that's again shown here in this Brahms case, but we also had pieces at about 0.5 and 8 notes per second. And we try to span the space as much as possible. All of these were classical piano pieces. In this case was Bach, Beethoven, Brahms, and Bach. There we go. And so the task for the subject was to listen to these sequences, and then occasionally there would be a pitch distortion in the task. And so they had to decide on each trial, was there a pitch distortion in the previous example, and did it go up or down? So I'll give you an example of the pitch distortion. Here's sort of a visual version of the stimulus. I don't have a good way visually to show you the distortion, but here, listen for the pitch distortion in this case and see if you can hear it. So if you heard it around the 6th second, you would be about right. So it tends to be a pretty difficult task for non-musicians, although musicians find this to be boringly easy. And so the question that we'll ask is, how well does the auditory system synchronize to this music? So I'll show you some data here. On the x-axis, what you're seeing is time. On the y-axis is frequency. And what I'm showing you is that here's a metric of neural synchrony, which we call intertrial phase coherence, which I won't explain now, but just sort of believe me when I say when it's redder, it's more synchronized, and when it's yellower, it's less so. And so what we see is that in the 8 notes per second condition, we have high synchrony at about 8 hertz. Similarly, at 5 notes per second stimulus, we see high synchrony at 5 hertz. But when we did the very slow condition at 0.5 notes per second, we saw very little synchrony actually at the note rate. Instead, what we see are these kind of large broadband responses corresponding to each individual note. Right? And so this is a very, at least qualitatively, different kind of response. And so we ran the study again with note rates just above the 0.5 per second condition to see, is this a gradual change or one that has a hard sort of boundary, sort of a range under which we no longer synchronize. So we did the study again, new subjects, and we have, again, a very similar finding. For the 1.5 notes per second condition, we see high synchrony at 1.5 hertz. For the 1 notes per second condition, high synchrony again at 1 hertz. But at 0.7 notes per second, we lose synchrony. And so this suggested to us, actually, kind of surprisingly, that this is a hard boundary here, where at which 1 notes per second and above we synchronize well, and below we don't synchronize so well. So what's going on here? There's music that exists here. What does it mean to not synchronize? And so I won't give you a great answer for this, but I want to give you an example of 2 different subjects, one that synchronizes well at this range and one that doesn't. And so I'll show you in black is the waveform, the acoustic waveform, and red is the trace from the MEG signal. Zoom in on a particular window here. What you can see is that for the top, the above subject, you have pretty nice synchrony, right? And so you can see that there's sort of a peaked response that happens almost exactly when each note occurs. And when you compare that to the lower subject here on bottom, you see sometimes he responds later, sometimes he responds earlier. And so he seems to struggle a bit more with synchronizing as well. So what is the major difference between these 2 subjects? I bet you can guess. The top one is a musician and the bottom one is not. And so this was just an example for 2 different subjects, but of course we did this for a group. And we found that for our musicians, we found much greater synchrony at all rates, and also that you expand your range of synchrony to include the 0.7 notes per second condition. So it actually is possible to synchronize at these rates. So here's just a sort of bar graph of this kind of plot, which shows this statistical effects. But we also found that it's not only a musical training effect, but also a perception effect as well. Right, so the more that you synchronize for the non-musicians, the more that they were able to synchronize, the better they were at detecting that pitch distortion that I discussed earlier. And so you can see that shown in this graph here. For the musicians, as I mentioned before, they were all at ceiling for this task, but what we found was that the longer that they'd been training, the better that they were able to synchronize for this task. And so this suggests a very tight coupling between behavior and synchrony, both in terms of training and perceptual performance. So what have I shown you for this first segment? First, that non-musicians show high synchrony to music above 1 note per second. Secondly, that music training improves synchronization and also extends the boundaries at which we're able to synchronize. And lastly, that synchrony relates to improved content processing. And this content thing is actually really important because the task is a pitch-based task. It's not a rhythm-based task. And yet the synchrony, which is decidedly a temporal kind of process, seems to affect what happens here. And so that suggests, again, to us, this idea of segmentation being an important process here. You have to know when things occur in order to know what they occur, what is going to occur. Okay, so that's section 1. So we show that the auditory cortex does track acoustic rhythms and is tightly coupled with behavior. Now the next question is this tracking supported by a neural oscillator or by some other kind of mechanism? So what are our options here? The first hypothesis that we're sort of proposing is that we expect that the synchronization effect should be a result of a neural oscillator. Another alternative, though, is to realize that, well, the input is rhythmic. You're giving the subject music. So maybe it's not so surprising that the output is also rhythmic. Then maybe you have responses to each individual note. And because those responses are sort of overlapping and moving on top of each other, it looks like an oscillation, but actually it's not. So I first want to highlight the team that helped me work on this project, both Florencia, Dana, Bijan, and David, who are all super integral in making this happen. So thanks to them for all their effort. I want to give you a sort of basic idea of what this means to live in an evoked world or an oscillator world. So here's a couple examples of the kinds of responses that you'll get from an evoked model given a kind of input. So in top here, I'm showing a particular input. And bottom, I'm showing the sort of evoked model's response. And what you can see is that it has a typical stereotyped response with a specific lag and sort of remains in this kind of space. Now, as you increase the rate of inputs, you'll find that the response is again the same. It has the same time lag, has the same shape. But because there's overlap, you start to see something that looks more and more like an oscillator. This is sort of the alternative hypothesis view. Now, what does an oscillator world look like? Well, an oscillator has its own temporal fluctuations, its own time constants, and so it sort of spontaneously moves on its own. And so the idea is that an oscillator should synchronize to the inputs that it's given. Here's an example where the note rate is just too slow. It's like the 0.7 notes per second condition, and it doesn't synchronize very well. Now, I'm showing you another example here where we speed up the note rate a bit, and you'll find that the oscillator starts to synchronize better and better. And so the question then is, these are two very different kinds of models, but from an MEGI view, they look very similar. And how can we actually decide which one we're seeing at each point in time? So one thing that we sort of noticed might be different is actually the phase of the oscillator or the evoked model at the time of the note input across frequencies. And so what you can see is that if you look at the slowest condition, this phase input is sort of closer to the second peak than it is to the beginning peak. But as you get faster and faster, the phase kind of advances closer and closer to the first one. Whereas in the oscillator case, you sort of seem to maintain yourself about in the sort of trough here. And so this is a sort of consistency of phase across frequencies. So in order to sort of boil that down into a more quantitative number, we can represent what we've seen in the sort of cyclic patterns in terms of one cycle. And now the angles that we've represented here are the actual phase differences between the inputs and outputs. And so these give you sort of two different kinds of measures of what we should expect to see. And so we can boil this down further into one number by sort of normalizing the distance here and averaging across these vectors. And because these vectors are very spread out, you get a very small number when you average. And because these ones are pointing in a similar direction, they all sort of work together and give you a longer vector. And so, okay, here's the point. We can distinguish these two models by analyzing phase across frequencies. And while that may seem like a practical difference that seems very small and quirky, it actually generates theoretical differences that are very big, right? So if we have an oscillator system, we have more of an ability to understand how we do prediction and segmentation, whereas evoked system is much more of a reactive kind of process. So let's go and try to generate some real quantitative predictions for our previous MEG data, right? So our previous study, we already had stimuli that had a wide range of note rates. And so the idea is to sort of give our new quantitative models these same stimuli that we had for our previous subjects, see how they do, and compare it to what we see in the actual data. So I won't explain what the models are, particularly right now. If you have questions about it, I encourage you to ask them. And I do have some slides that will explain them, but I think it's more useful to just show you how they behave. So the evoked model is one that sort of has a typical response, as I showed you before. And basically, each time as you get a note, you get this kind of response. And as you increase the note rate, you see that they start to overlap more and more until you see something that looks really like an oscillator. So when you look at the phase differences between the output and the input at a wide range of note rates from 0.5 to 8 notes per second, which are now color coded in these vectors, you can see that it actually wraps around the phase cycle all the way almost the near 360-degree effect. And so that's typified by this very small phase concentration measure that we see from the evoked model. Let's compare that to the oscillator model, where you have sort of a natural resting state fluctuation, which doesn't really synchronize at very slow cases, but as you get closer and closer to its natural resting state, which in this case is about 4 hertz, you see more and more examples of synchrony. And across all of these different frequencies, you can see that they stay within a sort of a narrower phase regime. And that gives you this an example of phase concentration that's much larger. So given these two possible predictions, what does our MEG data actually look like? So I'm showing you this here qualitatively, and you can see that there's kind of an in-between effect, right? So the frequencies from 1 to 5 hertz are very clearly in one range, but the 8 notes per second condition seems to span out into something different. And so, it's a little hard to tell from here. So we decided to do a more quantitative analysis. Now I'm showing you the oscillator model prediction and the evoked model here. And on the sides, I'll show you single subject examples of phase concentration. Just the length of these vectors. And what you can see is that, again, we're somewhere in the middle, right? The evoked model is clearly too low as a good predictor for this data, but the oscillator model, while it's within confidence, it's a little above what we would expect to see. So what can we conclude from this? The first point we can conclude is that the MEG data is more than reactive. It has to have some components to it which don't just respond to a specific time lag. But perhaps the result shows a combination of the evoked and oscillator mechanisms in the brain, right? So the claim is not that there are no evoked responses, but that there must be also something else. And so maybe this is representing that sort of milieu. So the idea would be then that if we can reduce the evoked response, we might be able to see something that looks more like an oscillator model. And one way to reduce the evoked response is to reduce the attack of individual notes. So the first example I gave you was drumming, which has a very sharp attack and will sort of generate very large responses. Another example, like a stringed instrument, will have much smoother responses, and it will generate less of an evoked response in the brain. And so we decided to generate new versions of these stimuli with where we can manipulate the strength of the note attack and see how that affects performance. So how did we do that? We took the sheet music that we started with and generated MIDI files for each one of them that tell us exactly when and at what pitch we should have each note. We then took a database of piano notes and created an original version and a smooth version. This is just by adding a gain function to the note. We can then place each one of these notes exactly where our MIDI file tells us to. We can sum them all together. We have a sharp attack stimulus, and I'll play you an example of that here. So sort of a honky-tonk version of the piece. Now here's the smooth version, where we've done exactly the same thing, just used a smooth version of the notes. So now you can hear something that sounds a bit more like a underwater accordion or something, right? And so now let me show you what the data actually looks like. I'm first showing you the sharp attack stimulus, which we should consider as something like a replication of the first example. This is all new subjects on new stimuli now. What you can see is actually a perfect replication, right? So we have the evoked response model is much lower than what we see in the actual data, and the oscillator model is sort of above, but looks pretty good. Now, when we smooth out the inputs, we see something that's really more in line with an oscillator model. Right? The right hemisphere is now significantly increased in phase concentration, and the evoked model really just is not in the right space for this. So what did we show here? We showed that phase concentration metric is actually a reasonable method to distinguish between oscillator and evoked models, which is good because it's a question that can come up not just in the auditory domain, but in any other perceptual system. We showed that the results are likely indicative of an oscillatory model rather than an evoked one. And lastly, that we can sort of shift whether we're in an oscillator state or in an evoked one, depending on different kinds of musical features. So the idea here should be that you could also do the other thing, right? Like, so you could also make a sharper version of the stimulus that's a bit more random, and you might see something that looks more like an evoked response, right? And so it's actually sort of these components that are sort of weighted depending on what's required. So what I've shown here is that tracking might be supported by a neural oscillator. I'm freely open to the possibility that there are other models that might better explain the data, and I'm very open to hearing suggestions for what those might be. So if you have ideas, please suggest them, and we can maybe collaborate together and figure it out. So the last question that I'll ask, before that, a brief aside. Did any of this matter? So if any of this actually matters, then it should be the case that removing these rhythms from speech should obliterate intelligibility. And also by adding in an artificial version of that rhythm, you should improve intelligibility a bit as well. And that turns out to be true. So this is one of the first projects I worked on with Oded Gitsa. And what we found was that if you actually remove, so I'm showing you first here an example of a typical speech perception task where you sort of listen to a series of numbers, for example. Now you can take the same sort of perfectly intelligible signal and filter out the syllabic rhythms, so anything from 2 to 8 hertz, which I'll show you here. You can see very slow things and very fast things, but not the actual signal itself. And you can also do a version where you sort of try to add in that rhythm again by basically adding clicks exactly where the peaks are in the original stimulus, right? So this is really just well-placed noise that you're adding here. What you find for subjects is that by removing these rhythms, you really show a big decrease in intelligibility overall. But by adding these well-placed noise, you can get some intelligibility back, which is, I think, pretty impressive. Now, what's also interesting is that if you do an MEG study, you can find that this change in intelligibility is mediated, also potentially mediated by a change in neural synchrony, right? So the difference that we see here in intelligibility correlates well with the difference in neural synchrony when subjects are listening to these two different kinds of stimuli, suggesting that it might be mediated by a neural oscillator, neural synchronization. Okay, so now let's get to the last part, the sort of question of, if we will believe that we're in an oscillator world, then we have to start to contend with what that means perceptually. How do we deal with things that aren't perfectly rhythmic? And so this is work that I've been working on with Florencia Aseneo, who's a new professor at the Instituto de Neurobiología in Mexico. Is a new professor there. If you have a chance to work with Florencia, do it. And if you don't, try to find a way to work with her. She's an amazing person. We've done really great work together. We have tried to start from a sort of very typical prediction-based task that has been done many times, which is to take a series of tones that are perfectly isochronous, perfectly the same interval at every moment in time. And then the last tone should be sort of a little bit early or a little bit late. And you ask the subject, well, is this tone early or late to you? Now, this work has generated lots of interesting theories about how prediction is done, including work that we've done, which has shown that your ability to actually detect delayed stimuli depends on the phase of a delta oscillation just prior to that stimulus. So that suggests that there is some synchrony involved here. However, it doesn't replicate the sort of typical thing that we actually see in the world. Things generally aren't perfectly isochronous. I've already given you some examples of this. In speech and music, while there is a peak at about 5 hertz, there's a wide range of variability here, both in speech and similar amounts in speech and music. So how does an oscillator actually deal with this kind of ambiguity? That's our major question. So we decided to take our simple basic task and add a bit of Gaussian jitter to it, right? So you just add a bit of temporal displacement for each one of these tones. And the questions that we'll ask is, what do listeners do? Why do they do it that way? And how do they implement it? So I'll start first with what do listeners do? And that's because even for me, the experimenter, I'm not sure what the expectation should be. And that's because there are 2 different ways of calculating this that are straightforward, at least. And they give you different answers on every trial. So here's one example. It's the SOA method, which is a terrible name. I apologize for that, but think of it as an interval method. And so what you do is you extract temporal intervals from each individual tone. You sort of save them up on a number line as a memory store. And then you take an average and you sort of extend that average from the last tone, and that should give you some expectation. Another way to do this is to not try to find exactly when each tone occurred, but try to infer when each tone was supposed to occur. Remember that we have some expected location for each place. And so maybe the idea is that you should infer the best expected location. And so this will actually give you a different answer and is more akin to something like linear regression, right? So for each beat number, you have a sort of recorded time and fit a line to that and extend the line further out. So what do subjects do? So we built this task. We roved the final probe tone around this range and generated and asked the subject, is it early or late to you? We can collect those responses, a bunch of 1s and 0s, and then try to fit a sigmoid either based on the SOA expectation or by the rhythm expectation. And in that case, see which of these models has a steeper slope, right? So if you have a steeper slope, then you have a more rhythm-like case in this case, right? So this subject is sort of a rhythm-preferred person. So we did this for 3 different experiments at 3 different rates, around 1.2 hertz, 2 hertz, and 4 hertz. And what we found, quite surprisingly, was 3 different results. So now I'm showing you there's a difference in performance for each one of these subjects. So if you're above the 0 line, you prefer the SOA method. If you're below the 0 line, you prefer the rhythm method. And what we see is that for the slowest condition at 1.2 hertz, you see a clear preference for SOA. At the faster rate, at 4 hertz, you see clear preference for rhythm. And 2 hertz, you're somewhere in the middle. So here your jaw should be dropped. We have no understanding of exactly why this should exist. And so we dug a bit deeper. And what we found was that it depends not only on stimulus rate, but also overall performance, how you do on both models, right? So the better that you're doing overall in this task, the more you prefer the SOA method, and the worse that you perform overall, the more you prefer the rhythm method. And so this difference of stimulus rate actually has more to do with your overall performance across this line, and that sort of generates a difference in method, which looks like it's a stimulus rate effect, but might just be a performance effect. And so this is sort of the what effect, right? You see this sort of significant dip below 0 and then an increase above 0 afterwards. We found that participants change their method depending on overall performance and stimulus rate. So the next question that you should ask is, why on earth would somebody do this? Why is this the right method to go with? And it actually turns out that the answer is because it's the right thing to do. It's the optimal thing to do. And that's optimal under a couple assumptions. One is that the brain measures temporal intervals with some amount of noise. It's not a perfect measuring system. And so even if I give you an interval at around 2.5 seconds, you're going to have some, let's say in this case, Gaussian noise that makes it more difficult for you to understand. Now, Another thing that you should assume is that on each tone that we hear, we should make a prediction of when the next tone will occur. So here's another example where I've sort of gotten to 3 tones, and I can make an expectation of the 4th tone because I know the intervals that have already occurred. And lastly, that we should combine our expectation and our sensory measurement to generate a final estimate of the timing of each tone. So this is a very typical Bayesian model of temporal prediction. Let's see very briefly what this looks like on a single trial level. So here's the first tone that you get in a trial. You measure it with some sensory noise. You should have no expectation. It's the first tone that you've heard. The same thing is true of the second tone because you still haven't heard an interval yet. And so you have, again, the same kind of estimate that's based purely on your measurement. However, on the third tone, now you've heard an interval. And so you should have an expectation where the most likely place that should occur is exactly the same interval that you've just heard. Right? And you should combine that with the measurement that you actually get. And so you can see now that your estimate has a bit more confidence and also a bit of bias towards the prior. And now as you add more and more tones, you get more and more confident in your prior because now you have more information about what's going on in the system. And so that will actually generate more and more bias in your estimate. Now, what happens when we actually build models that do this? You can have it do it in the sort of SOA way or the rhythm way. And we actually find that the SOA way looks a lot like what we actually see in the human data. We have a sort of a space here where you have sort of high noise in the system where you prefer the rhythm method. And when you are more precise, you prefer the SOA method. So the answer to this why do listeners exhibit this behavior question is that participants are actually acting in a manner consistent with Bayesian principles. When they can't rely on their sensory system as much, they rely more on the expectation for rhythmicity to sort of get them through the task. And so the last question that you might ask then is, okay, but how does the neural system actually implement something like that? And I don't have a perfect answer for you, but we went back to the same oscillator model that I showed you in the second section of this talk. And we basically, instead of feeding it music, we fed it trials of this experiment and see how it synchronized to the system. Now, an important parameter here in the system is this kappa value, which decides how much does this acoustic signal influence our oscillator. And so we rove that to see, okay, well, how do we get this kind of variance across these different inputs? Now, what you can do is for each trial, extract the phase of the oscillator at the sort of SOA expected time and the rhythm expected time, and see how concentrated are they relative to one another. And what you can see is that as you increase the coupling parameter, you sort of shift the oscillator sort of shift its method from preferring the rhythm to preferring the SOA. Now, the last thing that you can do is instead of extracting the expected location, you can extract phase at the time of the probe tone and have the oscillator actually do the task, using the phase as a means of predicting whether the tone was early or late. And again, it shows us very similar kinds of behavior where when you perform worse overall, you prefer the rhythm method. When you perform better overall, you prefer the SOA. So this gives you sort of the what, why, and how of this system. So it's suggesting that one potential mechanism might be something like an oscillator that allows you to sort of, to calculate phase adjustments across time as a means of generating something like a rhythmic prior. So just to summarize a bit of what have we learned from oscillators, the first is that we can use oscillators as a means to constrain the phase difference between input and output. And that can be very useful for aligning our sort of the best parts of our input with the most excitable moments in our neural cycle. And that can allow for things like temporal prediction, segmentation, and attention. Now, the other point that we found is that oscillators may be able to act as something like a neural heuristic for a rhythmic prior in ambiguous cases. So even though speech isn't perfectly rhythmic, an oscillator can still be useful. Now, why is that? It's because most times people think of oscillators as being sort of perfectly rigid sine waves where they sort of just like reset right to 0 every time they get an input. Now, this is a very rigid way of doing things, and it doesn't really provide you much computational power. But when you have something that's more sensitive, that has different kinds of phase responses depending on the phase of the input, you can get very interesting calculations across time, which can be very useful for things like prediction. So lastly, I just want to talk about a couple future directions for us. So the last thing I showed was a sort of stress test of the oscillator system. My hope now is to sort of fully break it and sort of study, how can oscillators deal with things like predictions that aren't rhythmic at all. And so one example of that is acceleration, which is something that actually occurs quite often. You hear like bouncing balls that sort of accelerate over and over again. And so we're starting to do some like tapping studies where subjects tap along to rhythmic and accelerated inputs. And we have sort of a little bit of data here showing sort of maybe some unsurprising results that when things are accelerating, you're a bit later, and when you're decelerating, you're a bit earlier. But actually are maintaining sort of stable error across time. And so that might be something a little bit difficult for an oscillator to actually replicate. And so our sort of goal is to sort of build models that do this kind of thing and see, does an oscillator still have a role to play here, or do we need to come up with something new? Lastly, we have a couple more questions. Now that we're doing tapping studies, what are the influences of motor inputs to prediction, which is a huge field that we want to take part in. And we want to ask more questions about how predictability and time and context affect memory. So the fact that you can predict something suggests that it's more compressible, so maybe you can actually remember it better. I've been doing some work with Omi Raka in the Popo lab, showing that sort of big changes in context can generate differences in order memory. And so I think there's interesting work to be done and to see how the role of prediction fits there. And lastly, to look at how these deviations from isochrony that we have in music and speech are meaningful, and to see how those connect with things like emotion and memory. The music is not isochronous for a reason, not just because it's lazy, but because it actually creates new and interesting ideas for us. And so we want to sort of delve more deeply into sort of more meaningful shifts from isochrony. So with that, I want to thank you all for listening. Thank you to my PhD labs with David Popel and Bijan Pesseron, my current group at the Institut Pasteur, and all the people that have helped me to get here. I just want to make one last shout out that this week is Black in Data Week, which is a really cool, awesome organization that is doing a bunch of events this week. So I encourage you to look into it, to follow the people that are posting for it, and to get involved, because it's really all about networking. So thank you very much.
Thank you so much, Keith. That was incredible. So we have we have many questions actually, and we have a few minutes to go through some of them. So I'm just going to start with those that have been upvoted. So the first question I have here is from Jasmine Kwasa, and she asked, do you interpret the individual differences in your phase concentration measure as each person's inherent strategy? So oscillation versus evoked model based on musicianship. And do you think you could train someone more into the evoked model regime with rhythm training?
Oof, what a great question. I haven't had that one before. Do I think it's a difference in it? I don't know. I think part of it is that different people have different kinds of evoked responses. And some of those evoked responses will look more or less like an oscillator. Because a lot of it actually has to do with the kind of time lag between the response and the input that generates a lot of this phase difference. And so it could be that it's just a purely biological feature and maybe doesn't have a input. But again, it also, I'm sure there must be some individual difference in terms of, how you actually weight between these two things. Actually, are they two different components or not? Or are they the same component that just sort of does different kinds of things? And so I think it's a great question, and I don't have a good answer, unfortunately, but I think, maybe that should be the next follow-up.
Evidence of a good question.
Yeah.
Okay, next is from Shade Abiodun. This is so interesting. She says, thinking about the smoothing of speech versus music, I wonder whether the effects when combined, I wonder about the effects when combined. For instance, highly stylized singing like jazz or opera versus more syllabically distinct rhythms such as rap, though one could argue that some types of rapping, mumble rap, for instance, are smoother. What might one expect from comparing the two?
So from comparing those two different kinds of
I think the question is kind of just about comparing opera, something more smooth like jazz and opera versus something like rap that has more has sharper rhythmic.
Yeah. So when you get to things like like some of the things that make rap interesting is, at least to me, I haven't studied rap from a scientific perspective. Um, but some of it is about the sort of rhythms that are involved, right? So it's not that they're sort of saying exactly the same, like it's not like the first version of our task, right, where things are perfectly isochronous the whole time. And so that's a feature that we haven't really baked into this quite yet in terms of like, everything that we're considering sort of generally has the same length over time. And so there might be other features that are involved in helping you to get to like, you know, 2-for-1 kinds of patterns, different kinds of rhythms, and different kinds of syncopations in particular that sort of make rap interesting. So the answer to this is certainly to study more rap and to study things that are not just classical music. As you know, I've shown sort of a bad example in terms of really only doing classical piano music, which I'm now trying to get out of. But it's just so much easier. But now we have to build that up. I think that's important. And so stay tuned. And it's but I think in terms of the question of speech and music specifically, when you have sung versions of music, there, I think the temporal statistics rely more on the music side than they do on the speech side, right? You're existing on a song rather than sort of doing your natural prose. And so there, I think there's sort of maybe a predominance for the music side.
Cool. And I think we have time for one more quick question, before
Sorry, I
we
went over.
transition over to the trainee Q&A. So this one is from Yulia Oganian. I'm sorry again if I'm butchering everyone's name. This is the problem with only seeing everyone's names written out. Yulia says, hi, Keith, excellent talk. If I understand correctly, in the 2019 study, you assumed smaller evoked responses to the soft attack stimuli. Did you actually test whether this is the case? In speech, evoked response magnitude reflects relative, not absolute attacks, so this assumption does not hold there, but music might be different.
Yes. Finally, someone's asked the question I have a slide for. So here what I'm showing is the different kinds of sounds, the sharp attack sound and the smooth attack sound. And here are the responses, the acoustic responses to those sounds. If you just sort of, at this point, we knew exactly when each note was, so you could do an average across them all. And so you can see very clearly that there's a drastic reduction in the evoked response for these signals. I would note that this is really more of a change in the sort of relative edge rather than like a volume shift. And as I understand Yulia's work, I think this would apply in terms of reducing the evoked response. But she can tell me if that's not the case.
I was going to invite Yulia to speak, but I realized that she cannot in this setting. So thank you so much, Keith. That was an incredible talk. We're going to transition now to the trainee Q&A. I'm posting the link one more time for anyone who missed it. And we're just going to move into this new Zoom room.
Great. Thank you guys so much.
There it is.